Alright, hi everybody. This is our Symmetry Safari project by Mike Bodie.
Eric Bottleson.
And Ethan Diorio.
Sam Birch is not here right now for this part. So we're going to start off with some line symmetry. And the definition of line symmetry is a line that runs through the center of an object, drawing, or shape. So in simplest form, it could be like a square, or you could have...
You could also have an octagon because you can draw a line through the center of it and it will be exactly the same on both sides of it.
Okay, so or in the more complex, you could have a shape more like this, where so you can cut it down here, 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 and it would be perfectly symmetric.
So our next section is circle symmetry, and circle symmetry is anything that has an infinite number of lines of symmetry. So for example, this side of a yo-yo has an infinite number of lines of symmetry because if you were to draw a line down any part of it going through the center, the two sides would be symmetrical. Now, when you go to this drawing, this does not show circle symmetry because as one circle, each of these circles, there are about 6 of them, they have circle symmetry, but once you stack them all up, then it takes away the circle symmetry and makes only one line of symmetry going right down the middle of this.
Alright, hi, I'm back, and this is circle symmetry again, and today we have car tire. Now you may be saying, no, it's not circular symmetry. Well, the inside part, the hubcap, is not circular symmetry. However, the tire on the outside is, if you take all this writing off of it. So, for example, if you split it down here, it has infinite number of lines. Like, if you remember, no writing. However, down in the hubcap, this is why the hubcap is not circular symmetry. Because if you take it down the hubcap, for example, like this, then one side has more of this part, than the other side. So that's why it may seem like it, but it doesn't.
This is another circle symmetry, but this is actually not circle symmetry. At first you might think it is, because it's circle, but it's actually not, because of these, you can only cut it 4 ways to make it circle symmetry. But a natural occurrence that is circle symmetry is this circle here. It's circle symmetry because you can cut it into infinity, like in infinite ways, and it would be symmetric. So this is Eric, and here's another example of actually this is our first example of opt art, and it's opt art because it uses circular patterns using a compass and straight edges to make the circles, and the squares making up the circles. This is opt art because it makes an illusion that these circles are converging into one circle, and they are actually not. They're separate circles, and that's the optical illusion.
Alright, hi, it's Ethan this time, and this is another example of opt art. This time we have some geometric squares, and they are all together with some little white dots inside them that make it look like, or appear to the eye, that it's a bulge in this square. So this is another example of opt art.
Hi, this is Mike, and this is an example of optical art because this shape was made by a compass and is used to look as if it's moving and that it's waving around just by the way that the circles are formed together with the lines that are drawn on top of them.
Okay, so the next part is knot designs, and knot designs are when you take your techniques like straight edges and compasses and create shapes that go in front of and behind objects. My knot design was this. It's not that cool, but it shows that objects go in front of and behind other objects, and that's mine.
Okay, so for my knot design, I drew something that looks like this, and I showed that the triangles, that they would overlap like here, and that it would actually like knot underneath it, and it looks like that they are all knotted up, which is what the point of a knot design is. Okay, so for an example of symmetric molecules, which are molecules that that contain lines of symmetry, such as this one, because there is a line of symmetry going through the first fluorine down through the boron, and this molecule would be called boron fluorite because it has 3 fluorine molecules and 1 boron molecule.
Our second symmetric molecule is this, which is has a line of symmetry going down here from here. Basically, and it's also rotational symmetry. It's C6H6, 6 carbons and 6 hydrogens, and that's that.